Today's goals are for you to learn Newton's second and third laws. More specifically, you will be able to describe an object's acceleration in terms of its mass and the net force acting on it. So that's Newton's second law. And you'll be able to predict the direction and magnitude of the acceleration caused by a known force. That's connected to that second law because it comes with a formula. And then in the third law, you will be able to identify action and reaction pairs. So that's the third law that we're going to talk about today. Okay? All right. Beginning with the second law. Both force and mass can have an effect on an object's acceleration. So the greater the net force on an object is, the more that object is going to accelerate. So stronger force, more acceleration, right? And the greater the mass of an object, the less that object accelerates. Again, this makes sense to us, right? If you have a bowling ball, it's not going to accelerate as much as a basketball when the same force is applied. Both of these things can be nicely and neatly summarized by Newton's second law. Newton's second law is that the acceleration of an object is directly proportional to the net force acting on an object and inversely proportional to the object's mass. An easier form of this than all of those fancy words that we just said can be written as a mathematical equation that looks like this. Force, or in that case, the Greek letter there means that the net force of an object is equal to the mass of that object times the acceleration of that object. So that means net force, m is mass, and that bold A there is our vector of acceleration. So you can see how they're written in the equation so that you can see that the net force is proportional to the acceleration and the mass is inversely proportional. Oops. Here's an example for you. Roberto and Laura are studying across from each other at a wide table. Laura slides a 2.2 kilogram book towards Roberto. If the net force acting on the book is 1.6 newtons to the right, what is the book's acceleration? So go ahead and use that formula that we just introduced. Try to work this problem. It's a pretty simple equation. I believe in you. And then we'll come back and we'll do it together. Okay, so we're going to take that equation. Our force equals, some force equals mass times acceleration. And we're going to plug in the things we know, or you can alternatively, you can just manipulate this and then plug in, or you can plug in and then do the math. However you want to do it, I always find it easier to manipulate it first. So acceleration equals the sum force divided by the mass. So then you can plug in 1.6 newtons. Just note that they gave us the net force. They won't always do that for you. Sometimes you will have to calculate the net force and then plug it into the equation. And so we practiced in the previous lesson calculating net force, right? Even when they're not acting in the same direction and you have to find the resultant. So you might have to find a resultant net force, then plug it into this equation to solve for one of these things, okay? But this time they were nice to us. They gave us the net force, and then they said 2.2 kilograms was the mass. So if you do that math, you should come out with somewhere in the neighborhood of 0.73 meters per second squared, because remember that newtons is kilograms times meters per second. So you should come out, or meters per second squared, so you should come up with the right unit. So there is your answer. Questions about how we got there? I feel like this is more straightforward than some of the other equations we've been working with. So we will move forward unless anybody has questions. All right, let's talk about Newton's third law. When you push open a heavy door, you can actually feel the door actively pushing back against you, right? And if you hit a ball against a wall, the ball moves backwards, and you can see that the force, or that the wall had to exert some kind of force on the ball, because anytime an object changes direction, there's a force, right? Newton took these two everyday experiences, right? The ability to feel objects exerting a force back on you and see objects exerting forces on each other, and he summarized them into what we call his third law. His third law says, if two objects interact, the magnitude of the force exerted on object 1 by object 2 is equal to the magnitude of the force simultaneously exerted on object 2 by object 1. And these two forces are opposite in direction. A lot of words. A much simpler way to say this is for every action, there's an equal and opposite reaction.
Can I write that instead?
I want you to write the whole thing there first, but I'm not going to expect you to provide that definition on the test. The easier way of thinking about it is for every action, there's an equal and opposite reaction. If I push on the wall pushes back on me. Those forces are equal in magnitude, but opposite in direction. Okay.
Yeah, I do that.
Sometimes these forces are referred to as action-reaction forces. For example, an action force might be a ball that's rolling across the floor, hits the wall, and the ball exerts a force, a push force on the wall. That could be your action force. And in that case, then the corresponding reaction force would be the wall pushing on the ball. A lot of times, a mistake that people make here is that they think that the reaction, because when we think of a reaction, we think of something happening because of something. So when they think of the reaction, they think the reaction is the ball moving, but that is not a force, that's a change in motion. The force responsible for that change in motion is the reaction force. It's important to note several more things about action and reaction forces, and I'm going to list them for you here, okay? Number 1, they are equal in strength. So the force with which I am pushing down on the ground is the same strength of force with which the ground is pushing back up on me, okay? Equal in strength. They are, however, opposite in direction. So I'm pushing down, the ground is pushing up. They are acting on different objects, and this is important because when you have things that are equal in strength but opposite in direction acting on the same object, then those forces are considered balanced, right? But because action and reaction forces they don't act on the same object, it is impossible for them to balance. It's easy to think in your brain, well, if every force has a force that's equal in strength and opposite in direction, then how does anything ever move? Wouldn't those just cancel out? And the answer is no, they don't cancel out because they're being exerted on different objects. Okay? My force is acting on the ground's force is acting on me. Therefore, my net force could still be great enough, could still not equal 0, and therefore I could experience motion. They happen simultaneously to each other. So it's easy because, again, our brains think action, reaction, cause, and effect. It's easy to think that the reaction force is happening after the action force, but this is not the case. They are happening at the same time. It's just easier for our brains to label one action and one reaction. But in the example that I gave above, we could just as easily label the wall's force as the action and the ball's force as the reaction force, because they're happening at the same time. So it's really a matter of convention which one you choose to label as the action force and which one you choose to have as the reaction. Let's talk about field forces, because we've already talked about them a little bit. Okay? Field forces also exist in pairs, but it may be a little more difficult for your brain to understand them. Okay? For example, the force of gravity on an object is a field force. Okay? It's the force of the Earth's gravity pulling on an object. So if that's our action force, then what's the reaction force? Well, there has to be an equal opposite force from the object affecting the earth. However, if I'm pulling on the earth with the same amount of force that the earth is pulling on me, but the earth is tremendously more massive than I am, the force that I exert on the earth doesn't matter. That'd be like an ant trying to move a bowling ball, right? The ant could be pulling on the bowling ball with the same strength that the bowling ball is pulling on the ant, but the ant is never going to move the bowling ball, right? That's what we're experiencing here. So the earth pulls down on you with gravity, you pull back up on the earth, but the earth doesn't rise up to meet you because it's millions of times more massive than you are. Okay, so your force doesn't really affect it, and its force affects you a lot. All right. Questions?